Welcome back. We have finished Unit 6, and if you remember, Unit 6 was really more about an introduction to Unit 7. We did a little bit of one and maybe some two-step molar conversions. Well, Unit 7 is all basically about stoichiometry. I know that word sounds pretty scary, but it's maybe hopefully not as scary as it sounds. But like I said, it is kind of an extension or a continuation from Unit 6. Now, what stoichiometry actually stands for is technically mole math. Um, Again, I don't know if that's Greek or what, to be completely honest with you. I should probably look that up. But it is basically math involving moles. Again, like I said, basically a continuation of Unit 6. But we refer to it as, affectionately I might add, stoichiometry. Now, a mole ratio is basically a number of moles. Let me just do it this way: a number of moles of, let's say, compound A over a number of moles of compound B. So it's two different elements or two different compounds, one on the top, one on the bottom, and it is the ratio of one to the other. Now, the only way we could really get that ratio is we must have a balanced reaction. It must be balanced. If our reaction is not balanced, we're not going to be able to get a mole ratio because basically what I have not told you yet is these numbers right here are actually your moles. So when we get a balanced chemical reaction, the numbers, the coefficients, if you will, that are in the front of the compounds are the moles, and we're going to use those numbers to make our molar ratio. Now, I do want to go back real quick and fill in this theoretical yield. Now, theoretical yield is what you calculate, okay? You'll see later in this unit where we're going to talk about an actual yield. An actual yield is, say you were to do the experiment and you actually do, well, the experiment, obviously, and then you get the result at the end. That's your actual yield, right? You did the experiment. A theoretical yield is what is calculated. So if we do a calculation, then we should be able to get a certain mass or number of moles, but that doesn't necessarily mean that we actually will. I'll explain later why that is not necessarily the case. But every time we do stoichiometry, we are calculating what is the grams of this compound, or how many moles of this compound, or how many atoms of that compound. That is what's called a theoretical yield, because again, we haven't actually done the experiment. We are just estimating based on the stoichiometric calculations. All right, so let's go ahead and get started on the bottom. So what we have here is what we call our very first step of stoichiometry, which we call mole-mole. Now, a mole-mole is basically a mole of one compound into moles of another compound. Again, very similar to our mole ratio, which I just referred to a minute ago. So we're going to be starting with moles of one thing, and we're going to be converting into moles of something else. And the only way to do that, like I said, is a mole ratio. So like I also said right here, is we have to have a balanced chemical reaction. So what I'm going to do right now is balance this equation, because if we don't balance it, we're not going to be able to get our mole ratio. So we have potassium carbonate yields potassium oxide and carbon dioxide. The K's are balanced, the C's are balanced, and guess what? The O's are also balanced because we have 3 here, and we have 2 there, plus 1. So that gives you 3 and 3. So that is actually already balanced, which is quite nice. All right, so now that we know that we're going to have a 1 to 1 to 1 ratio, or 1 mole across the board, what we're going to do is we're going to start with, as always, the only thing they give us to start with, which is this. So we're going to start with 15 moles of CO2. Okay, then I'm going to do my ratio. So again, mole of carbon dioxide, you already know from Unit 6 that I need to put moles of carbon dioxide there to cancel that out. That's extremely important. Now remember, as I go up from the denominator up to the numerator, I'm going to change something. Only one thing can I change. What we want are how many moles of potassium carbonate. So I'm going to put moles of potassium carbonate. Notice I'm not being lazy. I'm still writing my units and I'm writing my compounds. Remember, we're going to add many, many steps onto this. And if you're getting lazy now and not writing out the unit and the compound, you are going to confuse yourself, and you will definitely confuse me if you ask for help and I'm trying to help you, okay? So please don't be lazy. Write out the units, write out the compounds, okay? So now that moles of carbon dioxide will cancel, as you could probably already assume, we will be left with moles of potassium carbonate. And guess what? This is a nice simple one step. That's all we're going to need. All we need now is our mole ratio. So if we look at the balanced chemical equation, mole of K2CO3, there's K2CO3. So notice we have a 1 right here, right? So I'm going to put a 1 there. Mole of carbon dioxide. There's my mole of carbon dioxide. I'm going to put that right there. 1 mole of carbon dioxide because, again, it's a 1-to-1 ratio. Okay? If those numbers were something other than 1, then obviously I would put something other than 1. So now, to solve this, it's going to be quite simple because it's going to be 15 times 1 divided by 1, which, not surprisingly, is going to equal 15. So because, again, the chemical equation was a 1-to-1-to-1 ratio, if I have 15 moles of anything, guess what? I have 15 moles of all of them because it's all the same amount. Okay? So that's our very first example. Let's go ahead and go on to number 2. It says how many moles of water are produced when we have 5.55 moles of hydrogen is reacted with an excess of oxygen. Now, when they say an excess of oxygen, that doesn't really matter. They're just saying that we have more of it, therefore it's not really an issue, right? If you have too much, you don't have a problem. If you have too little, that is a problem, right? We'll get to that later. But notice at number 1, it says in a decomposition reaction. They're just explaining the reaction. Look at number 1. That is a decomposition reaction. So back to number 2. We need to balance this equation. The H's are both balanced, but notice the O's are not. Here we have 2. Here we have 1, so I'm going to have to put a 2 there. That balances my O's. I have 2 on each side, but I doubled my hydrogen, so now I have 4. So I need to put a 2 there. So now it's a 2-to-1-to-2 ratio. So now we have a balanced chemical reaction. So I'm going to start with the only thing they give us to start with, which is 5.55 moles of hydrogen. All right, then I'm going to do, again, put moles of hydrogen down here to cancel it out. What we're asked for is how many moles of water are produced. So I'm going to put moles of water up above it. Moles of hydrogen will cancel, and I'm going to be left with moles of water. That's going to be my answer right there, right? So let's do our molar conversion. So water, here's water. Notice the number of moles, the coefficient is a 2. Here's moles of H2. Moles of H2 right here is also a 2. Well, so there's my molar conversion. For every 2 moles of water, I have 2 moles of hydrogen. Now, I can go ahead and do 5.55 times 2 divided by 2. But those of you who are good at math know that basically, because this is on the top and this is on the bottom, they will cancel out. So guess what? I'm going to go ahead and do a shortcut, and it's going to be 5.55. Now, again, if you get your calculator and you do 5.55 times 2 divided by 2, you're going to get 5.55, okay? Again, the 2's on the top, 2's on the bottom, they cancel. Just like moles of H2 is on the top, moles of H2 is on the bottom, they also cancel. That's just, again, a little bit of a mathematical shortcut for you. But if you don't believe me, get your calculator out and double check. All right, the next thing we're going to do is number 3. Number 3, we have a chemical equation. I'm going to go ahead and balance that first. This looks familiar. I know I need to put not an arrow because that's random. I need to put a 2 there and a 2 there and a 1 there because we just looked at number 2 and it's the same thing. Actually, number 3 looks exactly identical to number 2. And, oh, it's not. Okay. So the only difference, I'm sorry, is this is hydrogen, this is oxygen. So pardon me. Got a little confused there. All right, moving on. So now we have a chemical equation that says how many moles of water are produced with 5.55 moles of oxygen is reacted with excess hydrogen. Again, the excess hydrogen is not an issue. We have too much, therefore it's not a problem. I have 5.55 moles of oxygen. So I'm going to go ahead and set up my equation here. Moles of oxygen to cancel out. And then they want how many moles of water. So moles of water. Okay, moles of oxygen will cancel, leaving me with, of course, moles of water. You guys should know this is patterned by now. Again, I have moles on top of moles. I need to get my molar conversion. Moles of water, there it is right there, it's 2. Moles of oxygen, there it is right there, that is 1. So, all right, so now I am going to go ahead and get my calculator just to make sure I don't mess this up. Again, the 2 and the 1 do not cancel out. 5.55 times 2 divided by 1, just to be correct, even though it's the same thing, is 11.1. There you go. So for every 5.55 moles of oxygen, you would have double that, 11.1 moles of water for that particular chemical reaction. Now, again, if that reaction was something different, that wouldn't be the case. But in this case, because we have a balanced chemical equation, it is. Number 4, how many moles of nitrogen is needed to produce 0.250 moles of ammonia? So again, the first thing we need to do is make sure this is balanced. So my N's are not balanced, nor are my H's. I could go ahead and finish my N's, but again, I want to fix my H's first because when you have 2 and 3, remember you want them both to be 6, right? 2 and 3 are both divisible by 6. So to get this H to be 3 or 6, excuse me, I have 3, I need 6, I'm going to put a 2 there. And this 2, I need to be 6, so I'm going to put a 3 there. All right, notice that fixes my nitrogen, so I didn't even need to do anything there. So it is a 1 to 3 to 2 ratio. All right, the problem again gives us 0.250 moles of ammonia. That's a 3, sorry. And then I'm going to go ahead and set up my equation for getting the numbers of the mole ratio. I'm not going to worry about that at this point. And then I'm going to ask how many moles of nitrogen, okay? Moles of ammonia will cancel, and I'm going to be left with, again, moles of nitrogen. All right, now I have moles on top of moles, so I'm going to use my balanced chemical equation on the bottom, or I'm going to do the top first. Again, it doesn't really matter, right? Moles of N2, there it is. There's the 1. I'm going to put a 1 right there. Moles of NH3, there's NH3 there. It's a 2, so there we go. So again, I'm going to pick up my calculator because I don't want to mess this up either. Point, I could probably do it in my head, but let's not, make a mistake in front of all you guys because you'll laugh at me. 0.250 times 1, which of course will be the exact same thing, divided by 2, and not surprisingly, it is exactly what I thought it would be. 0.125 moles of nitrogen. All right, guys, that's again what is called a mole to mole or mole stoichiometric calculation. Again, it's probably the very easiest of all of them. It's even easier than what we did in unit 6. But like I said, as we go through stoichiometry, we're going to be adding individual steps onto each other. So that again is how you change from one compound to another compound, or one element to another element, or an element to a compound, or vice versa. We're changing from something into something else, and the only way to do that again is through a mole-mole conversion. And again, the reason, just to refresh your memory, we do this is because the only way we can compare hydrogen to water or ammonium to nitrogen is if we have the same number of atoms. Therefore, we have to go through moles because remember, moles represent a quantity of atoms. All right, guys, as always, thank you very much for watching, and I will see you again soon.